to chapter 8 here. We're going to talk about gases. So in this chapter, we're going to learn about gases, gas laws, all that fun stuff. So let us get started here. So chapter 8 is about gases. And when we're talking about gases, we are talking about the state of matter where pretty much everybody has broken apart from one another. So they are flying around. And as they're flying around, there's lots of collisions that could occur, for example, between the gas molecules and the container that they are in. And that's what we sort of associate pressure with, which is a very common property of gases that we look at, which is pressure. And really, as we'll talk about here in this chapter, there's kind of three sort of variables that we kind of deal with a lot: pressure, volume, and temperature. So these are three sort of categories that we deal a lot with when we talk about sort of pressures, or sort of gases. So let's start with obviously substances that basically are gases under normal conditions. So under normal conditions, and what we're talking about here is sort of like kind of room temperature, if you will, that sort of condition. And that's usually 25 degrees and 1 atmosphere in pressure, and ATM is an atmosphere. It's a very common unit of pressure that we use a lot when dealing with gases. And under sort of normal conditions, and that's sort of normal type conditions, if you ever look at any sort of table that has values in it and stuff like that, those are usually the conditions we deal with, which is 1 atmosphere for pressure. If it's dealing with a gas, and 25 degrees Celsius is sort of the standard sort of temperature that we deal with. But under those sort of conditions, we do not see ionic compounds basically behaving as gases. And they really will not exist as gases, because ionic compounds, as we've talked about, are basically a cation, which is our positively charged guy, and our anion, which is our negatively charged guy. And it is that electrostatic attraction between those two that hold it together. Remember, there's no sharing of electrons there in an ionic compound. That electrostatic attraction is like a super strong attraction. And that basically means they are not usually under normal conditions going to find themselves going apart from one another. So when those two guys get together, they're basically held together. And under normal conditions, you will never find really an ionic compound sort of in the gas phase. Maybe you did this or will do this at some point. If you have like salt water, for example, and you heat up the salt water, the water part will evaporate. But the salt part, you could heat the heck out of it. Basically, it'll just start to look like it's melting. It really will not go into the gas phase or anything like that. And that's really because that pretty much is the strongest attractive force that you could kind of have, is that electrostatic attraction. Now, on the other hand, molecular compounds, which are kind of like covalent compounds, these are guys that are sharing of electrons. And when they do share electrons, they have a much different sort of effect. There are certain ones that are just gases up front, things like carbon monoxide, carbon dioxide, hydrogen chloride gas, ammonia, and methane. These are all sort of gases. But a lot of molecular compounds are actually solids and liquids at room temperature. The major difference between sort of covalent compounds or molecular compounds and ionic compounds is it's much, much easier to pretty much turn a covalent compound into the gas phase than it is an ionic compound. And that is because if we just take, for example, water is a molecular compound, and water, as we talked about with bonding, is actually a polar molecule. The oxygen side of water is more negative. The hydrogen side of water is actually more positive. And when two water molecules, for example, come together, there is that opposites attract, which is what is sometimes referred to as a intermolecular force. And in this particular case, this is what is known as hydrogen bonding. It is sort of the positively charged hydrogen is attracted to the negatively charged oxygen in the other water molecule. And that is what holds it together. And an intermolecular force is much, much weaker than an intramolecular force, which is what we have when we're talking about an ionic compound electrostatic attraction. So when we do go to heat something like water, what happens is basically the bond between the two waters there is going to break. And what you end up with is a water molecule that goes into the gas phase and another water molecule that also goes into the gas phase, which basically makes steam in that case. So because what we're doing with really covalent compounds or molecular compounds is basically taking advantage of the intermolecular forces, the forces that hold one molecule together with another, which is a lot weaker force than the actual force within a molecule, which is sometimes referred to as an intramolecular force. An intramolecular force is the actual force within a single molecule. So for example, if you look at something like water, it is the bond between the oxygen and the hydrogen. On each side, the covalent bond there, the sharing of electrons is an intramolecular force within the molecule. And that's always a much stronger force than an intermolecular force, which is this guy over here, which holds this whole water molecule together with this one. That is why when we heat something like water, we get steam, which is just water molecules together. If it was the opposite way around and we were to heat the water, what would happen is these bonds here would break if it was actually the opposite way around. And that would not be good because then you would produce hydrogen gas and oxygen gas while you're trying to make, pasta and boiling your water, which wouldn't happen, as you know, hopefully doesn't happen. So because this bond here and this bond here is much, much stronger than this bond here between the two water molecules, that intermolecular force is really the one that will break first. So unlike ionic compounds, it's much easier in a lot of cases to hold or turn those guys into gases. And a lot of gas molecules, organic molecules, for example, are gases. So you think things like methane, propane, butane, those are lots of first early sort of organic compounds. And they're held together by super weak intermolecular force. They're referred to as dispersion forces, which means it really doesn't take a lot of effort for them to break apart. And that's why we find things like methane, propane, and butane very commonly in the gas phase. And that's also why, and you'll get maybe some of this experience later on in the semester when you start doing the organic labs, a lot of times organic molecules, because they're held together by dispersion forces, which are really weak intermolecular forces, they go into the gas phase really easily. They're sometimes referred to as being volatile. And that's why a lot of times you work in the fume hood with those, because they go into the gas phase really well or pretty easily. And also why you keep like the Bunsen burner away from a lot of those things, because they're very, very flammable, because they can go into the gas phase really, really easily. So there are some substances, obviously, that does exist as gases under normal conditions. And we think about sort of our elements, this hydrogen, nitrogen, oxygen, fluorine, and chlorine. Those are all of our diatomic molecules, so our guys that come as twos. Those are gases under normal conditions. Ozone, which is O3, is also a gas. And then obviously our noble gases there in group number 8 would also be obviously gases. Those are sometimes referred to as monoatomic gases. They come as ones, basically. The other guys, obviously, they're hydrogen, oxygen, nitrogen, and so forth. They come as twos, and sometimes referred to, obviously, as diatomic molecules, which I think we talked about earlier on as well. And again, on the periodic table, this is pretty much where you find all your gases and our hydrogen on that side over there. So let's talk a little bit about the difference between two words that are sometimes used sort of interchangeably. A gas is a substance that under normal conditions would be found in the gas phase. And that's different than a vapor. A vapor is something that under normal conditions is either a solid or a liquid. So that is why when we talk about sort of water in the gas phase, a lot of times we may talk about it as being water vapor. And that's because water normally under normal conditions is a liquid. And when it goes in the gas phase, we call it water vapor rather than water gas, because it just kind of sounds funny, I think. But so we call it water vapor, steam, obviously, when it goes into the gas phase. So anything that is normally a gas, we call it gas. Anything that is normally not a gas but can be converted into a gas is basically what the word vapor basically means. So let's talk a little bit about units of pressure and how we measure pressure. One very common way that we measure pressure is through the use of a barometer. And a classic barometer, which most schools don't have anymore. I don't know if you have it still up there. It's been a long time since I went up the stairs to the laboratory. But a old school barometer was basically a pool of mercury. and you put sort of a glass tube in there, and the mercury would sort of rise in the tube. And that is basically how we would measure the barometer. The atmospheric pressure would push down on the mercury in the sort of container, and that would cause the mercury either to rise or kind of come back down if the pressure lessens. And there are a few different units of pressure, but there are 3 common ones that we deal with mostly in this class. 1 ATM is an atmosphere again. There's also 2 units of pressure. One is referred to as a torr, named after the guy who invented the barometer, Torricelli. And 1 mmHg. mmHg is millimeters of mercury, is basically what it is. And that's because originally our barometers were made of mercury, and you're measuring basically where the mercury is. And by the way, if you ever do see a mercury barometer, the meniscus is actually the opposite way. It goes upward instead of down. And what you typically would see on the glass tube there is a ruler. So you would measure it in millimeters. Most of the time, though, you probably measure in inches or centimeters of mercury and convert it to millimeters of mercury. But basically, there's a ruler kind of on the tube there, and you basically can measure about where it is. So numerically equal to each other is a torr and a millimeter of mercury. They are a 1-to-1 relationship, which means if you need to do the conversion, you keep the number, just change the unit, basically. It'll be the exact same number. The important number, though, is going from atmospheres to millimeters of mercury, or torr, are backwards, and that number is 760. So in 1 atmosphere, there is 760 millimeters of mercury and 760 torr. That means if you are starting in an atmosphere and you want millimeters of mercury or a torr, you're going to multiply by the 760. That will cancel out the atmospheres, give you millimeters of mercury or torr, which again is basically a 1-to-1 relationship. Or if you had millimeters of mercury or torr, you would divide by the 760. So the 760 is an important number to remember. It will be used a lot as you're doing a lot of these conversions. And again, that could also be a torr. It will give you an atmosphere. There are other units of pressure, which in this class we don't really come across too much, but there's things like PSI, which is pounds per square inch. There is bar, which is basically like an atmosphere. They're pretty equal to each other. There's pascals, and kilopascals are also very common units of pressure. But for us, I think this is the big 3 here that we'll probably see most of the time, which is atmospheres, millimeters of mercury, and torr. Any questions on that there? So here is a much better picture, probably what I drew there, but of a barometer. And again, you have this pool of mercury. And again, you would actually read from the top of the meniscus in this case, because it actually does go this way. And we do sort of measure it again in millimeters or centimeters or inches there in terms of the ruler. All right, so let's talk a little bit about those 3 sort of barriers: pressure, volume, and temperature, that we deal with a lot. We're going to talk about some gas laws here. And in some cases, we may keep one of these things constant and vary the others. In some cases, we may vary them all. It depends on sort of the law. So the first law we're going to look at is Boyles Law. And Boyles studied basically the relationship between pressure and volume. So he studied the relationship between pressure and volume, and he kept temperature constant. So if we just think logically about sort of the relationship of what Boyles saw here, if I have gas molecules that are flying around, and as they are colliding, that is what's causing the pressure we associated with it. If I have a very small volume and I have gas molecules in there, I would expect the pressure to be high or low. We would expect it to be high because the volume at which the gas molecules are flying is a very small one, which means we would expect an increase in the number of collisions. And because we see an increase in the number of collisions, we would expect the pressure to start to go up. Now that's opposite if you give everybody a lot more room to fly around in. So if you increase the volume, everybody has a lot more room to fly around in. That means it's going to take longer for collisions to occur. And because there would be less collisions, we would expect the pressure to come down. So basically the relationship that Boyles saw was as the volume went up, the pressure went down. And as the volume went down, the pressure went up. So this sort of inverse relationship, one goes up, one comes down. And he came up with basically this law here. And the relationship actually is this for a particular gas. If you take a gas and you measure for that particular gas any combination of pressure and volume together, when you multiply them together, you always get the same number for that same gas at the same temperature. So if you don't change the temperature and you measure a bunch of pressure and related volumes, you will always end up with the same number. So basically, they could put that together into what we call Boyles Law, which is our P1 V1 equals P2 V2 here. Now, in terms of the units, the pressures here can be any pressure unit you want, as long as they are obviously the same on both sides, so everything cancels out. The volume unit here as well can be any volume unit you want, as long as, again, they are the same on both sides, so everything cancels out. So that's the key here. By the way, we're going to see a number of gas laws here, and when we have an equal sign, and maybe we have some things on opposite sides of the equal signs, if you need to rearrange it and solve for something, basically, if you move it across the equal sign, it ends up in the opposite location. So if whatever variable you're moving was up on top, it will end up on the bottom. If it was on the bottom right, it would end up on the top left, and vice versa. So if you ever need to move something around to the other side to rearrange, basically will always end up in the opposite location of where it started with when you go across. So here's that sort of graph, or a graph of Boyles Law, pressure versus volume, and we can see at much smaller volumes, we have a much higher pressure over here. And as the volume gets bigger, it gives everybody a lot more room, lowering the collisions. We see that the pressure does start to drop here as we go across. So why don't we try one here? An inflated balloon has a volume of 0.55 liters at 1 atmosphere. It rises to 6.5 kilometers where the pressure is 0.4. Assuming that the temperature remains constant, what is the final volume of the balloon? Okay, let's take a look. So I would highly recommend, especially when you're dealing gas sort of problems, there'll be a number of gas laws that you might have to choose from. Obviously here we only have one to choose from so far, but there will be more here. A really good thing to do is just to kind of pull out the information from the problem. So here we have a volume that is 0.55 liters. We have 1 atmosphere. Again, atmosphere is a pressure. And I write that right, 1 atmosphere. We have, it rises to 6.5 kilometers, which is useless here. We are looking, we have another pressure that is 0.4 atmospheres, and we are looking for a final volume. So in this case, you can see you got kind of Boyles Law almost staring at you. And again, that's a really good way to kind of approach gas law problems. A lot of times, if you pull out the information, it will kind of lead you to the right sort of gas law to use. Doesn't matter which one you call ones and twos, it does not, as long as you keep the numbers together that go together. So I'm just going to call the first set ones and the second set twos. That means our P1 V1 equals P2 V2. Here we are looking for V2, so I want to bring P2 to the other side. Although it's not a fraction, it is written on top, which means P2 would go to the other side, and that would give me V2 is equal to P1 V1 divided by P2. We're basically dividing it to the other side is basically how we get there. We're going to put our numbers in, make sure everybody gets in the correct spot. That's going to be 1 atmosphere. 0.55 liters divided by 0.4 atmospheres. Atmospheres here will cancel, and that will get me 0.55 divided by 0.4, and we will end up with 1.4 liters in this case, as that is the unit that is left over. Any questions on that there? So we do want to maybe understand and make sure, things are going correctly in terms of our calculations. So here we do see the pressure started at 1 atmosphere, ended at 0.4. So in this case, the pressure went down, which means because this is Boyles Law, we should expect the volume to go up. And it went from 0.55 to 1.4. So that's all good in there. So again, understanding somehow how the relationships are can help make sure you didn't maybe inverse a number or something like that when you went to do it. Any questions on that there? Okay, so the next sort of relationship we're going to look at will kind of look at two other sort of variables. We're going to look at volume and temperature, and we're going to hold pressure constant. And we'll also look at pressure and temperature and hold volume constant. So Charles' law is a couple of things here. It is, he looked at the volume and temperature relationship, and he held constant pressure. And what he saw was as the volume went up, so did the temperature. So the reason for that is if I increase the temperature, for example, of my situation here, will my gas molecules move slower or faster if you increase the temperature? They should move faster because they're gaining energy, right? So that's basically what you're doing when you increase the temperature, they're gaining energy, which means if my volume didn't move, we would expect the pressure to go up because there should be a lot more collisions. So in Charles' law, what it wants to do is keep a constant pressure. So the way it's able to keep a constant pressure is as you increase the temperature, which means our gas molecules are going to fly around a lot faster and cause more collisions. To keep the number of collisions constant, what happens is the volume actually increases with it. And what that does is it gives everybody a lot more room to fly around in, and it keeps the number of collisions basically constant, and thus it keeps the pressure constant. The opposite is true here as the volume goes down when the temperature goes down. So when you decrease the temperature, the opposite is true. Everybody's going to have a lot less energy, which means if the volume doesn't move and you decrease the temperature, it's going to take longer for collisions to occur, and you would expect the pressure to start to drop. So once again here, to keep the pressure constant, the volume actually adjusts to allow the number of collisions to stay the same. So even though our gas molecules are moving slower, the volume comes in on them. That allows the same number of collisions to occur, and that keeps the pressure constant. So Charles' law is V1 over T1 is equal to V2 over T2. There is a similar relationship, which is a good one as well. That's Gay-Lussac's law. And that dealt with pressure and temperature, and it kept volume constant. And that's really what we were just talking about here. That is P1 over T1 is equal to P2 over T2. And this is at constant volume. So in this particular case, it's pretty much what we were just describing. If you increase the temperature, the volume is fixed, is not going to move. And because that volume won't move, those gas molecules are going to fly around faster. That's going to cause an increase in the number of collisions. And what we would see in that case is as the temperature increases, so does the pressure. And vice versa, as the temperature goes down, so does the pressure in that particular case. Again, because the volume is not going to move, as we lower the temperature, it's going to move slower, the gas molecules, less collisions, and we would see that pressure start to decrease. There is an interesting relationship that if you take any gas, pretty much, and you plot a graph of volume versus the temperature, every single graph, every single line that you would have for any of the gas molecules we may be looking at, they will all hit the exact same spot on the graph in terms of the temperature. They will all hit minus 273.15 degrees Celsius. That number is a number we use to convert to Kelvin, right? So to convert to Kelvin, you would add 273.15, and that would give you 0 Kelvin, which is known as absolute zero. So Kelvin recognized the nature of this, and basically what that means is every single gas problem that you do and every gas law that you use that involves temperature, they all need to be in Kelvin. So temperature always needs to be in Kelvin if you're putting it into a gas law. Even if they give you the temperature in Celsius and they ask for the answer in Celsius, you got to put it into Kelvin and do the calculation and then convert it afterwards. So once again, our temperature in Celsius plus 273 will give us our temperature in Kelvin. But 100% of anyone, you cannot go wrong, and you will go wrong if you don't do it. Every temperature needs to be in Kelvin for sure. So if it's a gas law, put it in Kelvin before you go into the gas law, obviously, in that case. Any questions on those gas laws there? All right. So let's take a look at one maybe here. There we go. In an experiment, 452 milliliters of a gas is used in a light bulb. It goes from 22 degrees to 187 degrees Celsius. What is the final volume here? Okay, let's take a look. So once again, if we pull out the information here, we obviously have a volume that is 452. We have a temperature that's 22 degrees Celsius. We have another temperature that's 187, and we are looking for a volume. So now that we got a couple of gas laws to choose from, clearly there's no pressure, so Boyle wouldn't work. There's no pressures here, so Gay-Lussac Law would not work as well. And that means here Charles' Law would be probably our right move. We do want to convert to Kelvin, so we want to do a 273 on each of those. And 22, that gives us a 295 Kelvin on that guy and a 460 Kelvin on that particular one. So in this case, we're going to call the first guys there are ones, or second ones are twos. So that's going to be V1 T1 equals V2 T2. In this case, we want to solve for V2, so we're going to send our T2 to the other side, so it's on the bottom. It should end up on top as it goes across, and that would give us V1 T2 T1 is equal to our V2 in this case. Again, we're basically multiplying T2 to the other side on that case. We're going to put everybody in the correct spot, hopefully. So that's going to be a 452 up on top, a T2 up on top, which is 460, and a T1 on the bottom, which is 295. Here, the Kelvin on top and bottom are going to cancel each other out. That's going to leave us milliliters as our unit. So 452 times a 460 divided by a 295er. We're going to get a 705 Kelvin in this particular case. Any questions on that? Well, yeah, like, because that's clearly not a volume, right? All right. Thank you very much. You know, if you got the right unit, you should throw it up there, perhaps. There we go. How about milliliters? Yeah, I know. Just, that secret test, that we like to do sometimes. Edit that out again. All right, edit that out of the video. All right, so that's going to be milliliters that's left up there on top, which would be good. We do see our sort of pattern that we talked about. Our temperature here increased, which means our volume that we solve for there should also increase. So it went from 452 to 705, which is good as well. Any questions on that there? I crossed out the right ones. That was half the work, I suppose. Right? All right. So there is another sort of gas law that you might come across, and that is our good friend Avogadro. Oh, wow. How do you think he feels about that? Avogadro's law? Right. So Avogadro, when we think of Avogadro, we think of his number, and that number equals a mole. Yeah, there we go. Yeah. So he has a gas law, which is V1 over N1 is equal to V2 over N2. And this is actually at two situations. This is constant temperature and pressure. So at constant pressure and temperature, V1 over N1 equals V2 over N2, and N is the number of moles, just like we would think with Avogadro's number. And V is volume here. So in terms of units, obviously volume can be any unit you want, as long as they are both the same volume unit on both sides. And N is the number of moles, obviously, and it does need to be in moles clearly on both sides there. There is sort of a relationship of Avogadro's law is basically as the volume increases, so does the moles of the gases pretty proportionally to it. So if you double the volume, you double the moles. If you kind of lower the volume by half, you lower the moles. So they're sort of related to each other in that sense. So personally, you probably won't use too much of it, but you might come across it somewhere, and that is Avogadro's law. Taking together all the gas laws we just talked about, our Boyles or Charles or Avogadro's law, it gives us a really important gas law, which is the ideal gas law, the granddaddy of them all there. And our ideal gas law is PV equals nRT. And when we look at PV equals nRT, a couple of things are different than the gas laws that we looked at before. The major thing here is it's just kind of one condition. There's like no two pressures, there's no two volumes, no two temperatures. The other really important thing is it is also the most restrictive in terms of units. So when you use the ideal gas law, you have to make sure everybody's in the correct units. Otherwise, you will get the incorrect answer, which you do not want. So let's talk about those units. The pressure when you use the ideal gas law, it has to be in atmospheres. So it's got to be in atmospheres. The volume needs to be in liters. N should be in moles. And T should be in Kelvin, like everything else. And the reason that they all need to really be in those units is because R is a constant and is what is referred to as the gas constant. And it has a value of 0.08206. The units are liters times atmosphere up on top, Kelvin times mole on the bottom. I personally use 0.08206 because that's what they beat into my head, and I cannot get it out as much as I try. But a lot of books and people will use a more rounded version of that number, which is 0.0821. You can use either one that you like there. They're both okay. The good news about the gas constant there is you probably will be given it, which it'll actually tell you what everybody else needs to be in. So if you ever forget, like, you know, what units everybody needs to be in, you probably will have this available to you. So just take a gander over there at those units. And again, they all need to be in those units for everything to cancel out. What's an ideal gas? It's a non-fake gas. No, I'm just kidding. An ideal gas is pretty much this. There's really two things that make something an ideal gas. And pretty much under normal sort of pressures that we deal with in most cases, around 1 atmosphere or so, most of the gases, the volume of the gas itself is pretty much negligible compared to the volume of the container they're flying around in. It's relatively small versus the area which they're flying around in. And because the gas is flying around, we think of it as uniformly sort of filling the entire container it's in. So a lot of times we don't even look at the actual volume of the gas itself. And a lot of times what you will see in problems is they'll talk more about the volume of the container that the gas is in. So that's one thing that makes something an ideal gas. The other thing that makes something an ideal gas is basically the idea that there is, under ideal conditions, really no interaction between one gas molecule and another. So even though there may be multiple different gas molecules flying around in the same container, there'll be no attraction between those gas molecules. There'll be no repulsion between those gas molecules. It's almost like they're in that container by themselves, even though there's other gas molecules basically flying around. So those are really the two main things that make something an ideal gas. The volume of the gas itself is negligible, it's basically 0. We look at the volume of the container. And secondly, there's really an ideal situation, no interaction between different gas molecules in terms of any attractive force or repulsion forces. Most gases that we deal with, frankly, all gases that we deal with in this class and most of your chemistry classes will be ideal gases. There are things that are called real gases that you do have to take those things into account, and it makes the ideal gas law have a very scary looking equation that comes up with it. That is a little bit different. So every gas that we see will be an ideal gas, and it will behave and follow this ideal gas law here. A couple of really other important things involving sort of the ideal gas law and a couple other conditions and things that we may come across is, first off, we'll start with STP. STP stands for standard temperature and pressure. And when somebody says, hey, this is happening at STP, they are actually giving you a temperature and a pressure value. So when somebody says this happened at STP, that means the temperature is 273 Kelvin and the pressure is 1 atmosphere. So, or its equivalent, 760 torr or 760 millimeters of mercury. So STP actually does give you basically two values, the temperature value 273 and the pressure is 1 atmosphere. They need to both be those values in order for it to be STP conditions. So if either one is not one of those, it's not STP conditions. A nice thing about those type of conditions is you could actually avoid using the ideal gas law if you wanted to, and you were at STP. And at STP conditions, and it does, once again, has to be at STP conditions, 1 mole of any gas will have a volume of 22.414 liters. So that is a conversion that you could use if you are at ideal conditions, or sorry, STP conditions. But if it is not 273 and not 1 atmosphere, you cannot use that conversion. So if you want the safe bet and make sure you don't use it incorrectly, you could absolutely go into the ideal gas law under any conditions. It could be STP conditions, non-STP conditions, doesn't really matter. If it is STP conditions, you just use the temperature of 273 in the ideal gas law, and you use the pressure of 1 atmosphere, and you just plug and chug in there and solve for whatever you're looking for. But if you want a shortcut and it is at STP, you could kind of use that and kind of sidestep the ideal gas law and solve whatever you're looking for. If we take the ideal gas law and solve for R, that's actually how we get the gas constant and put everything in for STP conditions. That is where we come up with our 0.08206 basically number. The pressure being obviously 1 atmosphere, the volume being 22.414, 1 mole, and obviously our 273 condition. Any questions on that there? All right, let's try one here. Calculate the pressure exerted by 1.82 moles of SF6 gas in a vessel that has a volume of 5.3 liters and a temperature of 69.5 degrees Celsius. Okay, let's take a look. So once again, we're just going to pull out the information. We are looking for a pressure exerted by 1.82 moles, so 1.82. We have a volume that is 5.43 liters, and we also have a temperature there of 69.5 degrees Celsius. Again, here you can see you pretty much have one of everything, which will eliminate pretty much all the other gas laws. And you can kind of see the ideal gas law kind of sitting there. Remember that you always have R available to you. It is most oftenly not given to you in a problem. So you just got to remember that you always sort of have that number available. In this case, we would use our PV equals nRT. And once again, these are basically both on top. So we're going to solve for pressure. We're going to send this guy to the bottom to the other side, basically, again, dividing by the volume to the other side. That would give us P is equal to nRT divided by V. In terms of units, we got moles, which is good. We got liters, which is good. And like normal here, we have Celsius, which is not good. So we do need to convert that to Kelvin. So I'll try not to drop that there. So our temperature in Kelvin would be 69.5 plus a 273, going to give us a 342.5 Kelvin. Now we really have everybody in the units we need. So our pressure here will equal our moles, which is 1.82, our R 0.08206 liters, atmosphere, Kelvin, and mole. Our temperature in Kelvin, all divided by our volume here, which is in liters, and that is 5.43 liters. In terms of the units here, we got liters on the bottom and top going to cancel. We got Kelvin to the right and on the bottom will cancel. We got moles that will cancel. That is going to leave us, I'm going to go with the right unit this time, which is atmospheres. That is a pressure, I'm told. And we're going to multiply everything on the top there. So 342.5 times 0.08206 times 1.82, all divided by 5.43. Gonna hit us a 9.42 atmospheres as our pressure there. Any questions on that there? What's that? You might have used the 0.0821. I don't know if that's what you did. Yeah, so it's okay. Yeah. Again, I personally always use this number. It's just like I said, what was speed in my head and I can't get out. So either one's perfectly fine. I would say more and more nowadays, a lot of people are using the 0.0821 version of it. But like I said, it's just in my head, so I always use it. So it's okay. Other questions? Okay. Now, a couple of variations on this and a couple of common conversions that you might have to do. It is also very common that the volume is given in milliliters. So that milliliters to liters conversion is used a lot with this sort of formula. A reminder, there are 1,000 milliliters in a liter. So that kind of conversion is used a lot. And also another very common sort of variation as well is you're not necessarily given it in moles, but you're given something in grams and you need to convert it to moles. And how we go from grams to moles, we use what? Not Avogadro's number, but we use, it is the molar mass from the periodic table. That's grams per mole. So that's also two very common conversions that you have to do a lot of times with the ideal gas law, in addition to obviously making sure your temperature is in Kelvin. That's kind of a always sort of conversion. Any questions on that? So again, those are two places where you might kind of have to remember those couple of things. All right. Let's talk then about changes that occur in all those variables that are variables. I'll spit that out, right? Our volume, temperature, and pressure. So if we actually take the ideal gas law and solve it for R, which is a constant, for two different conditions, we could actually set those guys equal to each other. And we get this sort of gas law here. But in most cases, if you don't pop open the top there, the number of moles of gases probably won't change. So usually the moles is kind of constant as well. And that leaves us, which is sometimes left over what's on the bottom there, which is sometimes referred to as the combined gas law. And the combined gas law is P1 V1 over T1 equals P2 V2 over T2. Now, pressure on this one can be, again, any unit of pressure as long, again, they are the same on both sides. The volume, same deal, any unit you like as long as they're the same. And our temperature here does need to be in Kelvin like all the other gas laws. So it does need to be in Kelvin. This is a really good gas law to know, because pretty much from this gas law, you could get all the other gas laws that we just talked about. So if you're going to invest your time in remembering, this might be the one to remember. So for example, just to show you that, if we take this gas law, I don't go too far there. So if we take this gas law and go P1 V1 T1 is equal to P2 V2 T2, and you come across a problem where it says something like constant temperature, our temperature is not mentioned, you pretty much take it out of this law and just scratch it out, and now you have Boyles Law. If you take this guy and you come across a problem where volume is constant, or there's no mention of volume or moles, you can take this guy out, and now you have Gay-Lussac's law. if you come across a problem and you take this guy, there we go. And there is no mention of pressure. You just scratch it out, and now you have Charles' law. So that one, pretty much, you just take out whatever's not mentioned, whatever is constant, and you pretty much got the gas law that you need in that particular case. So it's a good one to kind of remember. And again, just pretty much take out whatever is not there or is held constant. And you'll probably have any of those kind of 2 = 2 type ones. You could even use the more advanced version if you needed Avogadro's law that we talked about, and you could include the moles in it if you want. And you go, okay, well, pressure and temperature is constant. So goes pressure and temperature on both sides. And now you have Avogadro's law as well. So you could leave the n in there as well and take it out of all the other ones. But it's a good one to remember, and it will help you maybe get to all the other ones. So it's a really easy way to kind of remember all those other gas laws by just remembering pretty much one gas law. So if you commit to memory kind of this one, and again, like I said, take out whatever is not there or constant, and the ideal gas law, you pretty much have every gas law you'd ever need with those 2 sort of equations or formulas. Yeah. Any questions on how to do that there? Okay, so let's do one here. I will say this is the one that gives people the hardest time rearranging. Yeah, so let's see how our rearrangement works here. Let's try one. Consider a sample of oxygen gas at 27 degrees Celsius with a volume of 9.55 liters and a pressure of 2.97 atmospheres. The pressure is changed to 8.25 atmospheres and heated to 125. What is the new volume? So take a shot at it there, see what you come up with. Okay, let's take a look and see. So once again, I'm going to pull the information out. We got 27 degrees Celsius, which is a temperature. We have a volume that's 9.55 liters, and we have a pressure of 2.97 atmospheres. The pressure is then changed to 825. It also is heated to 125 degrees Celsius, and we are looking for a volume. So just by listing everything there, it should hopefully point you to the combined gas law. Obviously, that is the only one that has all 3 of those variables in there. So we definitely want to use our P1 V1 over T1 equals P2 V2 over T2. We just want to check on some units here. So we have atmospheres on both sides, so that's good. Once again, here we do need to do our temperature conversion. So if we convert this guy into Kelvin by adding 273 to it, that will give us 300 Kelvin. And if we do the same thing here by adding 273 to it, it would be 398, it looks like. We now have everybody in the correct units here. Again, you could call the first set here all ones, as long as all the numbers stay together that go together, and those guys too. In this case, we have P1 V1 T1 is equal to P2 V2 T2. In this case, we pretty much want to isolate our V2 by itself. And by the way, it needs to be by itself and on top, basically, to solve for it. So in this case, we need to take the T2 and move it to the other side. We also need to take the P2 and move it down when it crosses over. And if you do that, basically multiplying T2 to both sides and dividing by P2, that will give you a P1 V1 T2 is over T1 P2 equals V2. So again, moving this guy down, opposite location, moving this one up, which would be its opposite location. Any questions on that there? All right, now that we got everybody hopefully in the right spot, we want to make sure we actually put everybody in the right spot, which is a very common error people make. They kind of reverse some numbers. So P1 in this case will be 2.97. V1 is 9.55 liters, and we actually want T2 up on top, 398. Divided by our T1, which is 300 Kelvin, and our P2, which is 8.25 atmospheres. In terms of unit, Kelvin on bottom and top will cancel. Top atmosphere, bottom atmosphere will cancel. That's going to leave us units of liters when we're all said and done. And that is going to get us 2.97 times 9.55 times 398 divided by 300 hit equals, divided by 8.25 hit equals. And that's a 456 in terms of liters. In this case would be our new volume. Any questions on that one? So again, if rearranging may give you some trouble, you do want to take some time and figure out again how to properly rearrange it. The sort of non-mathematical way, it really is mathematical, but just move it to the opposite location basically as you go across the equal sign is the quick way to kind of do that. Any questions on that one there? Okay. All right, then the next thing we're going to talk about in terms of gases is what is referred to as Dalton's law of partial pressures. Sounds really scary, but not so much. It is basically partial pressures. So for example, the reason it is called partial pressures versus just pressures is if we have, say, this situation where we have just one gas molecule or one type of gas molecule in a container, as it is flying around in there, pretty much all the pressure in this case should be a result of really just that gas molecule, as it's the only thing basically flying around in that particular container. Now, if we took a mixture of gases, which is a very common thing, which is say we had gas A in there, gas B, and gas C flying around in there, the total pressure in this particular mixture of gases would be a result of the pressure caused by gas A plus the pressure caused by gas B plus the pressure caused by gas C in this particular case. These are what are referred to as partial pressures because they each partially contribute to the overall pressure of that container or that mixture. So those are partial pressures. So really what a partial pressure is just simply the pressure based on one of the gases in a mixture of gases and how much pressure is causing in that situation. So how do we calculate the pressure in a sort of mixture of gases? The most common way that you would calculate the pressure in a mixture of gases is our good friend, the ideal gas law that we just saw, PV equals nRT. And basically what you would do is you would solve the ideal gas law for each gas individually. So you would do it for gas A, which would be nRT over V. You would do it for gas B in my example, which would be nRT over V. And you would do it for gas C, which would be nRT over V. The good news is they're all sitting in the same container, and most likely that container is sitting in the same room, which means the temperature for all the gases are going to be the same. And because they're all sitting in the same container, the volume for all the gases will be the same. So what that means is essentially T and V in each of these ones that I just wrote here, they're basically the same number for all of them. You just need to make sure they're in Kelvin. You need to make sure the volume obviously is in liters. R is a constant for all of them, which means they're the same number for all of them. So really the only thing that usually will vary is the moles of each of these gases. And again, this is a very common place where, like I said earlier, you may have to take grams to moles using the molar mass to do that. But you basically would figure out the moles of each of the gases that are in that mixture, and then basically just put it into the ideal gas law for each gas separately. Once you get all three numbers, each of those would represent the partial pressures of each of those gases. You simply just add them together, and that will give you your total pressure of that particular mixture. Any questions on that there? I will come up with what I was going to tell you in a second, as soon as I remember it. You know, I'm getting old. That's what I was going to say. So the reason why we can do pretty much the ideal gas law for each of these gases is what we were talking about earlier. The idea of an ideal gas law is, although there are multiple different gases in a mixture of the gases, based on them being in ideal conditions, they're not going to interact with each other. So even though they are technically in the same container, we could almost treat them like they're in there by themselves. So that's why we could use the ideal gas law separately for each of these guys. All right, why don't we try one here for good time's sake? We want to calculate the partial pressure and the total pressure in a mixture of 5 grams of neon and 5 grams of helium. Helium from the periodic table, 4.003. And neon from the periodic table, 2018, I think. All right, so we're looking for 3 answers here. We're looking for the partial pressure of neon, partial pressure of helium, and the total pressure of both of them together. Again, they're all flying around in the same container. So see what you come up with here. Okay, so since we're getting to the end here, once you finish that up, we'll start with it next time and finish it up. Any questions on anything we talked about here today?